Hello and welcome to video lesson 9 on Poisson's ratio. Our learning objectives are to define lateral and longitudinal strain, to define Poisson's ratio, to solve problems involving Poisson's ratio, and to state the relationship between E, G, and nu for linearly elastic materials. So I want you to read Beer and Johnston's section 2.4 and 2.8 to go along with this lesson. So before we talk about Poisson's ratio, it's important to talk about what we mean by lateral and longitudinal strain. So for the lateral direction, we're talking about the direction that goes up and down. For the longitudinal direction, also the axial direction, we're going left and right. Now, longitudinal strain, we're going to call the same thing as we've always called epsilon, and that's just delta over L, the extension of the rod divided by the original length of the rod. However, for the lateral strain, what we'll notice is that as we pull on this rod, the rod is going to shrink, it's going to narrow, and it's going to have an initial diameter, and then it's going to shrink, and it's going to have a final diameter. And the lateral strain is the final diameter minus the initial diameter divided by the initial diameter. Now that we've defined longitudinal and lateral strain, we can also define Poisson's ratio. And that gets the symbol nu, and it is a unitless quantity. Because it is the ratio of two unitless quantities. It's the negative of the lateral strain divided by the longitudinal strain. Now, for all materials, nu is less than or equal to 0.5. For most practical materials, it's always going to be greater than 0.1, most of the time greater than 0.15. For structural steel, you would most likely have a Poisson's ratio of about 0.3, maybe a little less. And there's a relationship between the parameters E, G, and nu. And for linear elastic materials, only for linearly elastic materials, G is equal to E over 2 times 1 plus nu. So only 2 out of the 3 are independent because this relationship would always give you the third. So if you know G and E, you've implied a nu. If you know E and nu, you've implied a G. If you know G and nu, you've implied E. Now let's work an example problem. So we have a bar. It's got a 12 millimeter diameter. And E for the bar is 2.5 gigapascals. Nu is 0.4. And it's subjected to a tension of 400 newtons. We'd like to know what the change in length of the bar is and the change in diameter of the bar is. And we aren't given any of those directly, but we can use some of the relationships that we already know in order to find the things that we want. So one of the things that we can start with is Hooke's law that says sigma is equal to E times epsilon. And I also know what sigma is because that's just P over A, and I can find out easily what A is, and I know what P is. So if I was to plug what I know about sigma into Hooke's law and solve for the axial strain, which would be the longitudinal strain, I would have epsilon axial equals sigma over E, which is equal to P over EA. That would be 400 newtons divided by 2.5 times 10 to the 9th newtons per meter squared. I get that from the gigapascals. Giga means 10 to the 9th. Pascal is a newton per square meter. And then I would multiply by the cross-sectional area, and I would need to express my diameter in meters. and it would be squared. So I would have pi over 4 times d squared. So I would end up with a meter squared in that expression. And I would end up with an axial strain of 0.001415. Now, if I want to find out what the change in length of the rod is, which is a quantity that I'm asked for, the change in length of the rod, delta is equal to epsilon axial times L. So that would be 0.001415 times the length of 150 millimeters. And that would be a 0.2122 millimeter increase in the length of the rod. So that gets the first thing that I am asked for, the change in length. Now, the change in diameter, I need to use Poisson's ratio for that because that relates the lateral strain, which is a function of the change in diameter, and it relates that quantity of interest to the longitudinal strain. So the lateral strain, therefore, is equal to negative nu times epsilon long, and that's the longitudinal, and that's the change in diameter divided by the diameter. So the lateral strain is equal to negative 0.4 times 0.001415. And that gives me a lateral strain of 0.000566. Epsilon lateral is the change in diameter over the original diameter. So delta D, the change in diameter, is equal to epsilon lateral times D. So delta D is equal to negative 0.000566 times 12 millimeters. And that gives me a number equal to negative 0.006792 millimeters. So that is a decrease in the diameter of the rod. That's it for video lesson number 9.